Hello AP Chemistry and welcome to Chapter 19, Thermodynamics. So this is like part 2 to Chapter 5, where Chapter 5 we talk about enthalpy, right? We talk at great length about what enthalpy is, right? Where enthalpy is the amount of heat that's transferred during a given process, right? It defines whether a process is exothermic or endothermic. And this is like the back half of that, right? Because enthalpy, right, as an energy term, only describes a tiny part of what's happening, and there's actually this whole other part known as entropy, which Chapter 5 alludes to, that we need to discuss now that gives us a better picture about what's happening in a given chemical reaction in terms of the energetics, okay? So thermodynamics, thermochemistry, all of that just describes the energy relationships, the energy between your reactant versus your product, and whether or not that energy relationship makes your process thermodynamically favorable or thermodynamically unfavorable, right? So, for example, if this is my reactant, right, and this is my product, right, we understand that to go from reactant to product, right, energy has to go in, right? If instead my product were down here, right, we understand that that would mean energy is going to come out of my system and be released. Note that in chemistry terms, right, lowering energy is a good thing, right? Increasing energy, bad thing, right? That means we have to put energy in to make it happen, okay? Do be mindful. So this is all we're talking about here, right? Is we're talking about, is there energy required to go in, or on the flip side, is there energy that will come out? There's another part to this picture, right, which is the kinetics, right? We aren't talking at all about kinetics. Turns out that every reaction has a given activation energy, EA, right? Activation energy that has to be overcome, okay? So again, activation energy is the amount of energy needed to make an reaction actually go. It is the amount of energy or the energy hurdle that must be overcome before reactants can actually be converted to products. And this is what determines the kinetics of a reaction, right? Where kinetics refers to movement, right? So this actually determines whether or not a reaction is going to go and if it's going to go quickly, okay? There's another term called equilibrium, which we'll discuss a tiny bit at the end of this chapter, that sort of determines where a reaction actually stops, right? Macroscopically stops. Microscopically, it doesn't stop. But to us, based on what we can see, there is no more progression of the reaction, right? And those are topics we'll cover later, right? Kinetics and equilibrium we'll talk about more later, but for now this chapter mostly deals with what's the difference between these two, which really should make sense because we've been talking about state functions, right? How it doesn't really matter how we get there, all we're concerned is what's the difference between A and B, right? Where if this is A, this is B, this difference is all we really want to know, right? We aren't thinking about what all is required to get from A to B, okay? Going back to state functions. All right, moving along, let's talk about spontaneous processes. We all know what spontaneous means, right? Happening without an outside assistance. So if we look here, right, we all intuitively understand that if we open our hand, this is going to happen, right? This, not going to happen, all right? Likewise over here, based on our basic study of gas laws last semester and just life things that we know, we understand that if there's a gas in A and no gas in B, and we open this, it's going to fill up both containers, right? We understand that gases by nature take up all the volume allotted to them, right? They spread out and take up all the space. We also know that there is no situation where it would spontaneously all go back to the same container, right? This happens spontaneously, this does not, okay? Now to add a little bit of, a little more thought to it, right? We know that ice will spontaneously turn into water as long as, ding, 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 as long as we are above the boiling point, right? We also know that water will freeze and turn solid as long as, ding, 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 we are below the freezing point, right? So we understand that a lot of things are intuitively spontaneous, like this one, right, and this one. And a lot of things are spontaneous, but they have conditions, right? They are spontaneous if. They are spontaneous when, right? Which means that there has to be some something else that we're going to tie the concept of spontaneous to. I think it should be obvious what that other thing we're going to tie spontaneity to, but we'll get there in a minute. All right. So, before we actually get to tying together whether or not a process is going to happen on its own, we have to introduce a new term known as entropy, where entropy is symbolized with an S, okay? Now, here is a basic introduction to entropy, right? So kind of like the roots of entropy. For isothermal processes, what does iso mean? Same, right? So same thermal processes, meaning the temperature doesn't change. No change in temperature, okay? Which, for our purposes, the only processes that we talk about happening often with no change in temperature, right, are our phase changes. Which means that we are talking about being at the boiling point or at the freezing point, right? Where delta S fusion, right, fusion refers to our melting point. Because if we think about it from the other direction, right, it is fusing into a solid. But H fusion is melting. Vaporization, I think, is obviously the boiling. Okay, which means that this is obviously our melting temp. This is obviously our boiling temp. And this is the heat of fusion and heat of vaporization, which should look a little bit familiar because you saw these terms, I think, as a bonus in your Chapter 5 homework, where delta H of fusion, right, is simply the amount of energy required to make that phase change happen. Okay, so delta H of fusion is the amount of energy required to melt something. Delta H of vaporization is the amount of energy required to vaporize something. Okay, which means that we understand that this is going to be an energy term measured in joules or kilojoules, and this is our absolute temperature, which means Kelvin scale, which means that my units for S are always going to be joules per Kelvin. Now, can we report it in kilojoules per Kelvin? Sure. But just know that the standard unit is always going to be joules per Kelvin, right? Going back to the fact that we have to tie in our temperature, okay, in order for it to make sense. So, this gives us our basic introduction to the unit for entropy. Let's go ahead and do a quick practice problem. Kind of like our bomb calorimetry, these problems are just unit analysis. So here we have a temperature, right? The boiling point of ethanol. The word normal does have implication that we'll talk about in a couple chapters. It's molar enthalpy of vaporization. Molar enthalpy of vaporization, that is delta H vaporization, is equal to 38.56 kilojoules per mole. And we also, what is the change in entropy in the system when 68.3 grams of blah are condensed to liquid at the normal boiling point? Okay, so note that this says condenses to a liquid. So are we vaporizing it or not? Not, right? We are condensing. We are going backwards, which means that if we want to talk about that process, right, delta H of condensation, right, means this would be a negative. Be negative 38.56 kilojoules per mole. Yes? Okay, so let's go ahead and look at our math. We have our negative 38.56, and let's say you didn't remember that other equation. Even I know it was on the last slide, so most of you probably remember, but we know that this is the heat of vaporization, okay, or the amount of heat released when we condense, because that's an exothermic process, right? Anytime we reestablish connections, energy is released. Anytime we break connections, energy is required. Okay, so we have this, right? We also know, oh look, we have what do we have? We have some grams up here. We know that there are 68.3 grams, okay? It's like, all right, well, that's not incredibly useful on the front end, but if I know that I have, we can put that down here. So 68.3 grams of C2H5OH, right? We can turn that into moles. Right, and so we can go ahead and we know we have 24.02 plus 6.06 plus 16. So we have 46.08 grams per 1 mole. And so we have 68.3 divided by 46.08. And that's going to give us I forgot what the rest of the number was. 822. So here we'll take our 1.4822 moles of my compound, right? And we know that my moles now cancel, but we know still that entropy is energy per temperature. That's right. So we're going to take our 78.3 plus 273.15 to turn it into Celsius, to turn it into Kelvin, and this gives us our entropy change, right? So we're going to multiply and then we're going to divide, and that's going to give us our entropy change. Yes? Fantastic. All right. Next up, second law of thermodynamics tells us that for any spontaneous process, the entropy of the universe increases. Note that universe is not the same as system or surroundings, right? Universe is the sum of my system and my surroundings, right? So what this is saying basically is that entropy, right, unlike most of our other terms, like enthalpy, right, we say that, energy is conserved, right? It goes in and then it goes out. But we're saying here that if a process is spontaneous, happening on its own without any outside intervention, what that means is for that process to be spontaneous, the overall entropy of the universe must increase. Okay? We're going to define entropy momentarily, or what it means in terms of common use as opposed to what we just saw. Okay? The entropy of my universe increases. All right, we're going to stop here, pick up in the next one, defining what entropy means. Thanks for listening. Be good, and I'll see you soon. Bye.